Welcome to CECS 228. Today we're going to start a new section, the last section in our course, which has to do with graphs. And so part one deals with basic terminology and representations, and that's what we're going to be covering in this lecture video. So again, I do encourage you to have these set of lecture notes printed and ready before you continue to watch the rest of the video. So what is some common terminology? We're going to start off with graph. So graph G is going to consist of two sets. One of them will be a non-empty set V, which is going to contain all of the vertices or nodes of the graph. The set E is going to be a set of ordered pairs, and that is going to represent all of the edges of the graph. And so it's the set of ordered pairs Vi paired with Vj, where I and j are indices in the range of 1 to n. So we say that an edge is connected at its endpoints, and it's going to be connected by means of vertices. Now, a graph can either be directed or undirected. It's going to be directed if its edges have an orientation. So for instance, let's say that we have nodes V1 and V2 that are connected by a directed edge that leaves V1 and goes into V2. And that's the only edge that we have connecting the two nodes. Then in that case, we say that the edge V1, V2 is part of the set E, but V2, V1 is not part of the set of edges. That's in contrast to undirected. So in an undirected, the edges do not have an orientation, so that if you have these same two nodes, V1 and V2, and you have an edge connecting them, the edge V1, V2 would be representing the same edge as V2, V1, but we would consider those two elements as part of the set. Now, if a graph has both directed and undirected edges, then we call that graph, or we consider it to be mixed. An edge that maps a node to itself is called a loop, meaning both the first and the second vertices are the same. A graph is said to be simple if it does not contain any loops, and if every pair of nodes is connected by at most one edge. That's in contrast to multigraph. So for multigraph, we still don't allow for any loops, but we might have maybe one or more pairs that are connected by more than one edge. The number of edges that connect the same pair of nodes, and that is in the same direction in the case of a directed graph, is called the multiplicity of the edge. And so with a graph, we could have, for instance, a directed simple or maybe undirected simple. We could have a combination of those attributes, and those all receive their own type. So in table number 1, we can see what the terminology for those are, and we're going to be referring back to this when we work on example number 1. But I do encourage you to kind of read over these and see what these attributes are. Okay, so let's go ahead and take a look at example 1. For example 1, they want us to determine the type of each graph. So if I go back to table 1, I see that there are 3 attributes that are going to determine the type. So first of all, whether it's undirected or not, whether it has multiple edges, and whether it allows for loops. So I'll create a similar table here. One will be for which graph we're considering. The second will be for the type of edges, so directed or undirected. The third will be for the whether or not multiple edges are allowed. And then the last one will be for, actually we have 2 more. Well, I guess this is the last one for the attributes. The last one will be for whether or not loops are allowed. And then the last one will finally list what the type is. Okay. So let's start with graph A. We see that the edges are not directed. Directed usually look like graph C, where we have an arrow pointing the direction in which the edge is oriented. So it's not directed. Does it have multiple edges between any two nodes? The answer is no. Does it have any loops? Meaning, does it have any nodes that contains an edge mapping back to itself? The answer is no. So based on these three attributes, it's undirected, no multiple edges, no loops. That corresponds to the first type, the simple graph. Okay, so graph A is simple. Okay, let's take a look at part B. It's still not directed. It does have multiple edges. If we take a look at nodes A and B, there are two edges that connect those two. Same for C and D and B and D respectively. So the answer here is yes. We also have loops. We have loops at nodes A, B, and D. So for something that is undirected but allows for multiple edges and allows for loops, that would be the third option, which is a pseudograph, or the third type, which is pseudograph. Okay. And last one. This one we do have oriented edges, so that is directed graph. We have multiple edges. The nodes C, D are doubly connected. And then for loops, we also have one at C, another at E. So what type of graph is directed, has multiple edges, and allows for loops? That would be the directed multigraph. Let's focus for a little bit longer on undirected graph and some of the definitions associated to them. So we are going to look at take a look at what is adjacent, incident, and neighborhood, starting with adjacent. So let G be an undirected graph with set of vertices V and set of edges E. We say that two vertices are called adjacent, or sometimes also referred to as neighbors, if there exists an edge that connects them. Okay, so if there exists some edge U, comma V in the set E. Such edge is said to be incident with nodes U and V. So the adjacency happens between two nodes. The incidence happens between an edge and a node. Now the set of all neighbors of the vertex V is called the neighborhood of V. And so what that will look like is a capital N of V, that's the notation, and that is going to be the set of all nodes U in the set of vertices V, such that UV is an edge. Alright, now with that in mind, let's take a look at this definition. Degree. Again, we're going to assume that G is an undirected graph. The degree of a vertex V, which is denoted DEG of V, is the number of edges that are incident with it. And then a loop is going to contribute twice. Alright, so let's take a look at example number 2. This one reads, what are the degrees and what are the neighborhoods of the vertices in the graphs G and H, which are displayed below? So let's take it one at a time. We'll look at G, and we want to look at the neighborhood. So I'm going to create a table. First column, I'll have the vertex, and second column, I'll have the neighborhood. I'll just write it as N of V. And for G, we have, let's see, 7 vertices, A through G. So A, B, C, D, E, F, and G. And if we look at the neighbors of A, that would mean all of the nodes that have an edge with A. So that would be B and F. If we take a look at B now, B actually has 4 neighbors because there are 4 edges that connect to B. That would be A, C. I'll write these in alphabetical order. So it's A, C, E, and F. Okay, let's take a look at node C now. C has 4 neighbors. We've got B, D, E, and F. Then for D, we have only 1 neighbor, and that's C. For E, it has 3 neighbors. It's going to be B, E, and F. B, C, and F. And then for G, we have, for F, we have 3 neighbors. Okay, so now we're focusing here. We have A, B, C, and E. And finally for G, G is by itself. So this is actually referred to as an isolated vertex. It doesn't have any neighbors, so it's just going to be an empty set. Now they do ask for the degrees as well, and the degrees is the number of edges that are incident to a vertex. So let me just go ahead and create another column for the degrees. Okay, so now we're focusing back on A. So there are two edges that are incident to A, so that means that the degree of A is 2. Then if we take a look at B, we have 1, 2, 3, 4. Take a look at C, we've got 1, 2, 3, 4 as well. If we take a look at D, there's only 1. Take a look at E, there's 3. Take a look at F, there's 4. And G has 0. So in this case, because we didn't have any loops, the degree agreed with the size of the neighborhood of each vertex. We're now going to take a look at graph H, and I've already gone ahead and drawn the table and listed the 5 nodes that are part of it. So we're going to take a look at the neighborhood of A, and A has 4 edges, but notice 2 of those are to the same neighbor E. We also have an edge to D and an edge to B. And here I've kind of broken the rule that we were writing it, or not the rule, but just the convenience of writing it in alphabetical order. But you could also write this, because in a set the order doesn't matter, you could also write this as BDE. Okay, let's take a look at B now. And B has a loop, so we need to make sure to write that B is a neighbor with itself. We also have a neighbor of A, so we have AB. It's also a neighbor with C, neighbor with D, and neighbor with E. So basically with all of the nodes of the graph. Okay, and then for C, we've got only 1 edge. So only 1 neighbor, and that's B. For D, we have several edges, but neighbors are A, B, and E only, and some of those edges are repeated, specifically between D and E. And then finally E, we have 3 neighbors, A, B, and D, as the edges go out to those 3 nodes. Okay, now this is where it's going to get a little bit interesting. So the degree of A, if we take a look at how many edges are incident to A, it's 4 edges. So the degree of A is 4. If we take a look at how many edges are incident with B, well, we have 1 with A, 1 with E, 1 with D, 1 with C, and then 2 with itself. So it actually has a degree of 6. Then if we take a look at C, there's only one edge that's incident to it, and that's the one that connects to B, so that's a degree of 1. So what is the degree of D? So D has 1, 2, 3, 4, 5 edges that are incident to it. So that means that the degree is 5. And last one, we have node E. So we're focusing now here. And how many edges does it have? Well, how many edges incident does it have? So it's 1, 2, 3, 4, 5, and 6. So that means it has a degree of 6. Okay, we're now going to take a look at a theorem. It's called the handshaking theorem, which says that if you have a graph G that is undirected and it has m edges, meaning the size of the set E is m, then the sum of the degrees of all nodes in V is going to be 2 times the number of edges. Okay, so written more explicitly, let's just say that V consists of vertices V1, V2, down to Vn. Then this theorem is saying that if you take V1 plus V2 plus all the way down to Vn, excuse me, and that should be degrees of each of those. So degree of V1 plus degree of V2 down to degree of Vn, that should give you 2 times the number of edges. Okay, and then there's a corollary to that theorem that says an undirected graph has an even number of vertices of odd degree. And we're actually going to prove the corollary, not the theorem, but the corollary we are going to prove. So what the trick to this is to separate the set of vertices into the set of vertices that have even degree versus the ones that have odd degree. Okay, so we're just gonna let V1 be the set of all vertices, let's call them Vi in the original set V, such that the degree of Vi is even. And we're going to define V2 to be the set of all vertices, Vj and V, such that the degree of Vj is odd. Now, from the handshaking theorem, which I'm going to abbreviate HST, so by the handshaking theorem, the sum of the degrees has to be equal to 2m, 2 times m. But we can break this up into the sum of the degrees of nodes that are in V1. So let's just write it this way. Plus the sum of the degrees of nodes that are in V2. Now, since the degree of all of the vertices in V1 are going to be even, when we take the sum of all even numbers, we're going to end up with an even result. So that means that this first sum is going to be 2 times some integer. Let's just call it q. Okay, plus the sum v in V2, degree of v. And I'll write the justification here on the side. So because the sum of even integers must be even. Okay, Okay, so notice what we have now. We have that 2m will be equal to 2q plus the sum of all of the vertices, or the sum of the degrees of all of the vertices in V2. So if we solve for that, that means that we're going to get the sum of degrees of nodes in V2 is going to equal 2m minus 2q. And that is an even number, right? Because that is a 2 times m minus q, where m and q are integers. Now notice what's happening here. We're adding odd numbers, right? These degrees of nodes in V2 are all odd. So we're taking the sum of odd numbers and ending up with an even result. The only way that can happen is if you have an even number of those odd numbers. Otherwise, if you have an odd number of odd numbers and you add them together, you're going to continue to have an odd result. So that means that we have an odd number an even number of odd terms. Because that is the only way that we can end up with a sum that is even. We're now going to take a look at example number 3, which reads, find the sum of the degrees in the vertices in graph H, then verify the handshaking theorem and its corollary. So let's go back to graph H, which we have here in example 2, and they want us to find the sum of the degrees of the vertices. So I'll go ahead and write it here, write the sum, and then we'll just transfer over since we have all the work. So the sum of the degrees of nodes in V is going to be the sum of 4 plus 6 plus 1 plus 5 plus 6. So that's a 10, 11, 16, 22. So we're going to transfer this result over to the back. We want to verify the handshaking theorem and its corollary. So let's start with the handshaking theorem. The handshaking theorem takes into account the number of edges. So we'll go back to page number 3 and count the number of edges on graph H. So starting with the ones that are incident to A, we have 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, and 11. We have 11 edges. Okay. And if we take 2 times that amount, we're going to get a 22, which is the same as the sum of the degrees. So that verifies the theorem. Okay, now as far as the corollary is concerned, corollary says we should have an even number of vertices with odd degree. So again, if we take a look at the degrees here, there are only 2 nodes that have an odd degree, C and D, and that is an even number of vertices. So I'll write this as degree of C was 1, and degree of D was 5. And those are the only nodes with odd degree. Okay, so again, because it's only two nodes, 2 is an even number, so that means that the corollary is verified in this example. Okay, now excuse me, we talked about undirected graphs. Let's talk about directed graphs, beginning with the definitions adjacent to or from and initial or terminal vertex. So we're going to let G be a directed graph. If there exists an edge u comma v in set of edges, then u is said to be adjacent to u, whereas v is said to be adjacent from u. So it's a subtle difference. U goes to v, you can remember it that way, and v came from u, or if that helps you remember. Now, given the edge u comma v in E, vertex u is called the initial vertex, and v is called the terminal or end vertex. Okay, we also have this definition of in degree and out degree. So if G is a directed graph, the in degree of a vertex v, which is denoted as degree with the minus symbol of v, is the number of edges with v as a terminal vertex. The out degree, which is denoted degree with the plus symbol, is the number of edges with v as an initial vertex. And then a loop is going to contribute 1 to both the in degree and the out degree of the vertex. So let's apply those definitions with example number 4. They're asking us to find the in degree and out degree of all of the vertices in graph G. So I'm going to create a table. First column will be for my vertices. Second one will be for the in degree, and last one for the out degree. And we have 6 nodes, A through F. So starting with A, we have one that comes in from A, then a second one that comes in from E, and that's about it. So the in degree of A is 2. The out degree of A, we have one that goes out from A, so then we have one that goes out to C, out to B, and out to E. So that's a total of 4. Okay, and one thing that you can do to verify that these numbers, it's a good hint that it might be correct, is to make sure that they add up to the total number of edges that are incident to A. So what I mean by that is if this were an undirected graph, how many edges are connected to A? We have 1, 2, 3, 4, 5, 6. So that means that the sum of the in degree and the out degree should add up to 6. And in this case, 2 plus 4 equals 6. So that's a path in the right direction, a step in the right direction. Okay, let's take a look at vertex B. So for B, we have 2 that are incoming, 1 from A, 1 from C, and 1 that is outgoing, and that's going to D. So we look at the number of edges that are incident to B in the undirected version of the graph, it's 3, and 2 plus 1 is 3. Okay, we'll move on to C. C has 1 incoming from A, another incoming from itself, and a third one incoming from D. So that's 3 for the in degree. Then there is 1 outgoing from itself, and 1 outgoing to itself, and 1 outgoing to B. So that's 2. And if we think about, or we count how many edges are incident to C, we have 1, 2, 3, 4, 5. 3 plus 2 is 5. Next, we move on to D. Okay, D has 1, 2 that are incoming, and 2 that are outgoing. E has A and D that are incoming as well as itself. So that's 3 incoming and 3 outgoing to D, A, and itself. And the total number of edges is 6. 3 plus 3 is 6. So that looks good. And the last node, F, is an isolated node. It has no it has no incoming edges, so that's a degree of 0, and no outgoing edges either, so that's an out degree of 0. Okay, and then we have this theorem, which reads, let G be the set of vertices and edges E, and it's going to be directed. Then the sum of the degrees of the incoming edges, or the in degree, is going to be the same as the sum of the out degrees, and that should be the same as the number of edges. Okay, so let's see. For example number 5, we have to verify theorem 2, the one we just read, for the graph G from example number 4. So I'm going to come back to this page, and like I mentioned earlier, we're going to transfer over the results afterwards. So I want to first start by looking at what is the sum of the in degrees. So the sum of the in degrees is going to be a 2 plus 2, which is 4, plus 3, that's 7, plus 2, that's 9, plus 3, that's 12. The sum of the out degrees is going to be 4 plus 1, that's 5, plus 2, that's 7, plus 2, that's 9, plus 3, that's 12. Now if we take a look at the number of edges and refer to the graph for that, we're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that's 12 edges. And if we take a look at the theorem tells us the sum of the in degrees will be the same as the out degrees, will be the same as the number of edges, and that's precisely what we're seeing here. So we're going to take just these 3 statements, transfer them over to the back. And that verifies the theorem. Okay. We can now talk about representations of graphs, or what different ways are there for representing a graph. We're going to start with an adjacency list, and we'll see how to create an adjacency list for both undirected and directed graphs. So for an undirected graph, it's going to have 2 columns, where the first column consists of all of the nodes, and the second column will be the list of the adjacent nodes to each node in the first column. In a directed graph, the first column will be the same, but the second column will be the list of the terminal nodes to each node in column number 1. And so let's illustrate it with example number 6, where they're asking us to create the adjacency lists for the given graphs. And starting with the graph on A, we have 5 vertices. So let's just go ahead and create that table. First column will be for the vertex, for the vertices, and second column will be for the adjacent nodes. So A, B, C, D, and E. This is very similar to finding the neighbors. The only difference is that we are actually not creating a set, we're creating a list. So if we take a look at what is adjacent to A, we have B, C, and E. If we take a look at what is adjacent to B, we only have A. If we take a look at what is adjacent to C, we have A, E, D. What is adjacent to D? We have C and E. And then what is adjacent to E? We have A, C, and D. What about for B? Well, for B we have still 5 nodes, same one. Now we're going to take a look at the terminal nodes for the second column. Okay. So if we look at A, we would want to focus on the outgoing edges. So A goes to B, it also goes to C, it goes to D, and it goes to E. If we take a look at B and focus on the outbound edges, there is one going to D and one going to itself. So B and D. If we take a look at C, C has an outbound going to A, an outbound going to E, and an outbound going to itself. And next we look at D. D has no outbounds, so none. And then if we take a look at E, E has an outbound going to B, going to C, and going to D. Another way to represent graphs is using adjacency matrices. So we're going to take a look at what is an adjacency matrix for undirected graphs, first for simple and then for multigraph. So the GB is simple graph with n nodes, then the adjacency matrix is going to be an n by n matrix where the ijth component will be a 1 if the nodes vi and vj are connected, meaning there is an edge between v1 and vj, vi and vj, and 0 otherwise. Now if you have a multigraph instead of a simple graph, then the adjacency matrix is still going to be n by n, where the ijth entry will be m if vi, vj is an edge, and it has multiplicity m, 0 otherwise. So to get a better idea of what those definitions are stating, let's take a look at example number 7. In this case, they want us to draw a graph with the given adjacency matrix. And they don't tell us what the nodes are, so I'm just going to go ahead and label these V1, V2, V3, V4. And same here for the columns. And because remember, we want, or matrix rather, is going to represent whether or not there is a connection between the two vertices. So I'll draw V1 as a node here, V2 as a node here, V3 as a node here, and V4 as a node here. Okay. So there is, and remember, we're still considering undirected graphs. Okay, so the direction doesn't matter. Is there a connection between V1 and V in itself, meaning is there a loop? The answer is no, because we have a 0. Is there a connection between V1 and V2? Yes, because we do have a 1. So we'll have this edge here. Then is there a connection between V1 and V3? There is. There is a 1. A connection between V1 and V4? There isn't. There's a 0. Then for V2, we don't really need to consider the first column because we already, combination of V1 with V2, or an edge between V2 and V1, we would have already graphed when we came across V1 with V2. Okay, in fact, if you notice, if you look along the main diagonal, all of the elements are going to reflect about the main diagonal. That's because this is undirected and there's really no distinction between the edges. Unless you have multiple edges. But in this case, there's only zeros and ones, so we're looking at a simple graph. Okay, so that means that I would only need to worry about looking at V2. Is there an edge from V2 to itself? The answer is no. Is there an edge from V2 to V3? Answer is no. Is there an edge from V2 to V4? Answer is yes. I'll draw this a little bit more to the left. Okay, next for V3, we would only need to consider V3 with itself, and that's a no. V3 with V4, that's a yes. And finally for V4, we would only need to consider V4 with itself, and well, that's a no. Alright, so that is for G. Let's take a look at H now. H, we have elements 3 and 2, so that means that we're looking at a multigraph. We still have 4 nodes, however. So V1 doesn't loop back to itself. It does connect to V3 and it's to V2, and there are 3 edges that connect to V2 because we have a multiplicity of 3. So that's 1, 2, and 3. Does it connect to V3? Nope. Does it connect to V4? It does, and it connects doubly. So we need 2 edges. Okay, then again, we don't really need to consider V2 with V1 because it was already considered here in the first row, V1 with V2. We just need to consider V2 with itself, which is a no, V2 with V3, which is a yes, and there's only 1 edge. Then V2 with V4, which is a yes, and that's, again, 1 edge. Now we look at V3 with itself, and that is a yes, actually, so that means we're going to have a loop. V3 with V4 is a yes, and we have double edge. It's doubly connected. Then we don't need to consider V4 with V1 because that we took care of here, or V4 with V2. We just need to consider V4 with itself to be on the lookout for any loops. But we don't have any loops, which means that we just have this final graph. Another type of representation that we can use for undirected graphs is incidence matrices. So an incidence matrix on an undirected graph G with n nodes and m edges is going to be an n by m matrix, which we're going to call AG, and that is going to be the matrix of elements Aij, where Aij will be 1 if edge j is incident to vertex I, or 0 otherwise. And again, we're going to take a look at example number 8 to get a better idea of what that definition is saying. So in this case, we're given the graph, and we have to come up with the incidence matrix. Notice that the number of rows corresponds to the number of vertices, whereas the number of columns corresponds to the number of edges. So in our case, we have 5 vertices and 6 edges. So we're going to have a 5 by 6. And so I'll make sure to have 5 rows, 1, 2, 3, 4, 5, and 6 columns. And here on the side, just as a reminder as to what these rows represent, They represent the vertices V1 through V5. And the columns represent the edges E1 through E6. Okay, so now we take a look at vertex 1 and see which edges are incident to V1. That would be edge 1 and edge 3. So that means that at the first row, first column, we would have a 1, and at the first row, third column, we would have a 1, and then zeros everywhere else. Next, we take a look at V2 and see what edges it's incident to. It's incident to edge 3, edge 4, and edge 5. So that means that row 2, column 3 has a 1, row 2, column 4 has a 1, and row 2, column 6 has a 1. Everything else will be a 0. Next, we look at V3. V3, we have two edges, E5 and E6. And that means that we have a 1 here, a 1 here, zeros everywhere else. Okay, for V4, there are two edges, E1 and E3, that are incident. So 1 here, 1 here. Sorry, that's E1 and E3, not E4. So we'll just move over the 1. Zeros everywhere else. And then finally, V5, we have incident edges 2, 4, and 5. So 2, 4, and 5. And that would be our incidence matrix for this graph.